Hello, everyone! Today, we are diving into a really powerful concept, the limits of composite functions and variable changes. This is where your calculus skills really start to shine. Think of function composition as a chain reaction. What happens to the first part affects the next, and so on. In this chapter, we're going to master how to look at the big picture by breaking down complex functions into simpler ones. We'll learn the variable change tool, which is like a magic key that simplifies the most unreadable expressions. Sometimes we'll hit roadblocks called indeterminate forms, but don't worry, I'll teach you all the algebraic tricks, like factoring the highest degree or using conjugates to get past them. Let's get started. You've got this. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Exercise 1. Let f be defined on the interval from 0 to plus infinity by f of x equals the square root of the expression 1 plus 1 over x. We want to determine the limit of f of x as x approaches plus infinity. A. Write f as the composition of two functions, v circle u, specifying the functions u and v. B. Calculate the limit of u of x as x approaches plus infinity. C. Copy and complete the equation. The limit of f of x as x approaches plus infinity equals the limit as u approaches something of something, which equals something. All right, let's solve this together using our chain reaction strategy. Step 1, identification, or what I like to call dismantling. We need to look inside the function. Notice how 1 plus 1 over x is sitting comfortably under the square root? That's our inner function, u of x. So u of x equals 1 plus 1 over x. What's left on the outside? Just the square root. Let's call that our outer function, v of capital X, which equals the square root of capital X. Easy so far, right? Step 2, intermediate limit calculation. Now, let's see what happens to our inner function as x zooms off to positive infinity. We know that 1 over x goes to 0, so 1 plus 1 over x goes to 1 plus 0, which is just 1. This means our new variable, capital X, is approaching 1. This is the crucial link in our chain reaction. Step 3, applying the theorem. Finally, we look at our outer function, the square root of capital X, as capital X approaches 1. The square root of 1 is just 1. Synthesis. Putting it all together, we've shown that as x goes to positive infinity, the limit of f of x is 1. Great job! You've just mastered your first composite limit. Exercise 2. Let f be defined on the interval from minus infinity to 2 inclusive by f of x equals the square root of the expression 2 minus x. We want to determine the limit of f of x as x approaches minus infinity. A. Write f as the composition of two functions, v circle u, specifying the functions u and v. B. Calculate the limit of u of x as x approaches minus infinity. C. Copy and complete the equation. The limit of f of x as x approaches minus infinity equals the limit as u approaches something of something, which equals something. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Now, let's tackle exercise 2. This one is all about managing signs at infinity. It's a common trap, so stay alert. Step 1, decomposition. Just like before, let's find the inner and outer parts. The inner function, u of x, is 2 minus x. The outer function, v of capital X, is the square root of capital X. Step 2, study the inner function. this is where we have to be careful. We are looking at the limit as x goes to minus infinity. If x is a huge negative number, then minus x becomes a huge positive number. So 2 minus x will approach plus infinity. See how the sign flipped? Our new variable, capital X, therefore approaches plus infinity. Step 3, justification and final limit. Now, we just need to know what happens to the square root function as its input goes to plus infinity. Well, the square root of a huge number is still a huge number. So the limit of the square root of capital X as capital X goes to plus infinity is plus infinity. Synthesis. By following the chain, x goes to minus infinity, which makes u of x go to plus infinity, which makes the square root go to plus infinity. We find that the limit of f of x is plus infinity. Keep up that momentum. Exercise 3. Let f be defined on the interval from -3 to 0 by f of x equals the cosine of the expression pi divided by the sum of x and 3. We want to determine the limit of f of x as x approaches 0. A. Write f as the composition of two functions, v circle u, specifying the functions u and v. B. Calculate the limit of u of x as x approaches 0. C. Copy and complete the equation. The limit of f of x as x approaches 0 equals the limit as u approaches something of something, which equals something. Let's bring in some trigonometry for exercise 3. Don't let the pi scare you, it's just a number. Step 1. Identify the argument. The argument is just a fancy word for the inner function. Here, u of x is pi over the expression x plus 3. Our outer function is the cosine function. V of capital X equals cosine of capital X. Remember, cosine is continuous everywhere, so we can just plug in the value if there's no problem. Step 2. Limit of the argument. As x approaches 0, we simply replace x with 0 because there's no 0 in the denominator to stop us. So x plus 3 goes to 3. That means our inner limit is pi divided by 3. Step 3. Final limit by composition. Now we take that result and feed it into our outer function. We need to calculate cosine of pi over 3. Looking at our unit circle, remember those 60-degree angles? We see that the cosine of pi over 3 is exactly 1/2. Result, the limit as x approaches 0 of f of x is 1/2. You're doing fantastic. Trig limits are no match for you. Alternative method. Exercise 6. Let f be defined on the interval from -infinity to 2 inclusive by f of x equals the square root of the expression -3x plus 6. By setting capital X equals -3x plus 6, determine the limit of f of x as x approaches -infinity. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's look at an alternative method, which is often called the direct change of variable. Think of it like putting on a pair of glasses. It gives you a new perspective on the problem. The problem gives us the change directly. Let capital X equal -3x plus 6. This allows us to rewrite our complex function f of x as a much simpler one, the square root of capital X. Step 1. Where does the new variable capital X go? Let's track its movement. As x approaches -infinity, the term -3 times x becomes very large and positive because a negative times a negative is positive. Adding 6 doesn't change that, so capital X approaches plus infinity. Step 2. Calculation with the new variable. Now we just look at our simplified function. Since capital X is going to plus infinity, we seek the limit of the square root of capital X. which is also plus infinity. Synthesis. Just like that, by changing our viewpoint, we see that the limit of f of x as x approaches minus infinity is plus infinity. This masking technique is a real time saver. Exercise 7. Let f be defined on the interval from -1 inclusive to plus infinity by f of x equals x minus the square root of the expression x plus 1. A. Explain why, when trying to determine the limit of f of x as x approaches plus infinity, we arrive at an indeterminate form. B. Show that for all x greater than 0, we have the square root of x plus 1 equals x times the square root of the expression 1 over x plus 1 over x squared. C. Deduce a factored form of f of x. D. Determine the limit of f of x as x approaches plus infinity. All right, heroes, it's time to face a big boss, the infinity minus infinity indeterminacy. It might look like a dead end, but we have a secret move, the algebraic ruse. Part A, the dead end. When x goes to plus infinity, both terms, x and the square root of x plus 1, go to plus infinity. Subtracting them gives plus infinity minus plus infinity, which is indeterminate. We can't say it's 0 because we don't know which infinity is stronger yet. Part B, the algebraic ruse. To compare them, let's factor under the root. Inside the square root, we can write x plus 1 as x squared times the expression 1 over x plus 1 over x squared. Why x squared? Because when we pull it out of the square root, since x is positive, it becomes x. Now we have x times the square root of the expression 1 over x plus 1 over x squared. Part C, final factorization. Now we can factor x out of the entire expression for f of x. It becomes x multiplied by the expression 1 minus the square root of the expression 1 over x plus 1 over x squared. Part D, the final calculation. Let's see where everything goes as x goes to plus infinity. Both 1 over x and 1 over x squared go to 0, so the square root part also goes to 0. This means the whole parenthesis 1 minus root approaches 1. Conclusion? We are left with the limit of x times 1 as x goes to plus infinity, which is plus infinity. We've successfully navigated the indeterminacy. Amazing work. Exercise 8. Let f be defined on the interval I from 0 exclusive to 1 inclusive by f of x equals the square root of the expression minus x squared plus 1 over x. Determine the limits of f at the bounds of the interval I. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Now, let's study a function at its interval bounds. Our interval is from 0 to 1, open at 0 and closed at 1. We need to check what happens as we approach 0 from the right, called 0 plus, and as we approach 1 from the left, called 1 minus. Case 1, limit at 0 plus, the open bound. Let's look at the expression under the root. Let's call it capital X. As x goes to 0 plus, minus x squared goes to 0, but 1 over x blows up to plus infinity. So their sum, capital X, goes to plus infinity. Since the square root of plus infinity is plus infinity, our final limit at 0 plus is plus infinity. Case 2, limit at 1 minus, the closed bound. This one is simpler. As x approaches 1, minus x squared goes to minus 1, and 1 over x goes to 1. Their sum goes to minus 1 plus 1, which is 0. Since we are in the interval, our expression capital X is positive, so it approaches 0 from the positive side.
The square root of 0 is just 0. See how different the behavior can be at each end? Always check your bounds carefully.
Exercise 9. Let f be defined on the interval from 3 inclusive to plus infinity by f of x equals the square root of the expression x squared minus 3x minus 2, all divided by x. Determine the limit of f of x as x approaches plus infinity. We've reached the final challenge, the algebraic masterpiece. Here we have plus infinity over plus infinity, which is another indeterminate form. Time for our favorite trick, extract the dominant term. Step 1. Factoring under the root. In the numerator, the x squared is the boss. Let's factor it out inside the root to get x squared times the expression 1 minus 3 over x minus 2 over x squared. Step 2. Simplify. Since x is going to plus infinity, it's positive, so the square root of x squared is just x. Now look at that! We have an x in the numerator and an x in the denominator. They cancel each other out perfectly. Step 3. The final strike. We are left with just the square root of the expression 1 minus 3 over x minus 2 over x squared. As x approaches plus infinity, those fractions 3 over x and 2 over x squared both vanish to 0. We are simply left with the square root of 1. Synthesis. The limit of f of x as x approaches plus infinity is 1. Bravo! You've successfully used every tool in the shed to master limits of composite functions. I'm so proud of your progress.